When you look at the stars, are you seeing the present, or are you witnessing something that happened long before your grandparents were born? This question first occurred to me on a quiet night when I stepped outside and let my eyes adjust to the dark. The sky looked motionless, permanent, almost timeless. And yet, everything I was seeing had already happened. The light from each star had crossed vast distances to reach me, carrying information from a different chapter of the universe's past. In reality, you and I are already travelers through both space and time. The Earth moves around the Sun. The Sun drifts through the Milky Way, and the galaxy itself drifts among countless others. All of this motion continues whether we notice it or not. If we could step outside our short human lifespan and watch the night sky on the scale of hundreds of thousands or millions of years, we would see the constellations melt and rearrange. Nothing above us is as fixed as it appears. Tonight we will trace how starlight preserves the past, how Einstein uncovered the link between space and time, and how moving close to the speed of light reshapes our sense of distance and duration. We will see why high-velocity travel pushes a traveler forward in time, and why starships arise not from fantasy but from physics itself. And we will follow these ideas back to the origins of our solar system, shaped by collisions, probability, and immense spans of cosmic time. The constellations seem so steady that it is easy to assume nothing about them ever changes. The Big Dipper returns each night in roughly the same place. Orion rises in winter as if it had been anchored to the sky since the beginning of time. But the moment you ask why those patterns remain recognizable, the illusion begins to unravel. If every star is moving through the Milky Way with its own speed and direction, why do the shapes not distort before our eyes? And if they do change, why has no one alive ever witnessed it? The short answer is that the stars are in motion, but the timescales involved are far longer than a human lifetime. Each star has what astronomers call a proper motion, its slow drift across the sky, relative to more distant background stars. This drift is typically measured in milliarcseconds per year, far too subtle for the naked eye. For most of history, observers could not detect this motion at all, which contributed to the long-held belief in a fixed celestial sphere. The modern understanding is different. Every star in the sky is a sun moving along an orbit around the center of the Milky Way. Those orbits are not coordinated. One star may be traveling slightly faster, another may be drifting inward or outward relative to the galactic center. A third may be swinging around on a path inclined to the others. Over millions of years, these small differences accumulate, and the familiar patterns we draw begin to stretch and deform. Until recently, this concept remained somewhat abstract, because the changes were too slow to visualize. That changed with the European Space Agency's Gaia mission. Gaia is building a three-dimensional map of the galaxy by measuring the positions, distances, and motions of well over 1 billion stars. It can detect shifts in position equivalent to watching a person walk across a continent from thousands of kilometers away. With this data, astronomers can simulate the sky far into the past and far into the future. Those simulations show that constellations are temporary arrangements. The Big Dipper, perhaps the most iconic northern pattern, is not a real group of stars moving together. Its 7 familiar points lie at different distances and follow different trajectories. Some are moving toward us, others away, and several slide sideways relative to the rest. Run Gaia's data forward by a few 100,000 years, and the Big Dipper becomes unrecognizable. The long handle bends out of shape. The bowl loses its symmetry. A culture living on Earth 1,000,000 years from now would not naturally draw a ladle from those stars. Orion faces the same fate. Its bright blue stars, many of which are young and short-lived, evolve quickly. Some will drift apart, others will leave the main sequence entirely. Over geological time, Orion will dissolve into a new pattern, and the hunter our ancestors admired will fade from the sky. The deeper truth is that constellations exist only from our particular vantage point. They depend on where we are in the galaxy. Move the observer even by a few dozen light years, and the pattern changes. A star that seems to form a corner of a familiar shape from Earth may slide far to one side when viewed from another system. Stars that appear unrelated here may line up neatly there. If a civilization were observing from a world orbiting a different star, their constellations would have no resemblance to ours. They would connect different points of light into different stories, because the geometry of their sky would be entirely their own. So the constellations we teach, depict, and name are not features of the universe but cultural interpretations. They persist only because we live too briefly to see them change. To the galaxy, a constellation is a momentary alignment, a snapshot in a longer process of motion. Human history is simply too short to reveal the shifting patterns. This understanding leads naturally to a deeper question. If constellations are temporary in space, determined solely by our position and the slow movement of stars, then what about time? The stars lie at different distances. Some are tens of light years away, others hundreds or thousands. If their positions in space are temporary, perhaps the images we see are also temporary in time. Light does not reach us instantly. It takes time to cross the void. From here, the next step is almost unavoidable. If the sky is a moving structure, and if starlight travels at a finite speed, then the night we see is not only a spatial pattern but a temporal one. Some of what we observe happened recently. Some of it occurred long before humans existed. To understand the sky honestly, we must ask not only where each star is, but when its light began its journey toward us. Stand under a clear night sky, and it is tempting to believe that you are seeing the universe as it is right now. The stars feel immediate, almost present in the moment with you. But if you ask a simple question, when did this light actually leave those stars? The view changes. You realize that what feels like now is really a collage of many different thens. I remember the first time I understood that clearly. It was disorienting. It still is, and I think it should be for you and for me. The key is that light has a speed, and that speed is not infinite. In empty space, light travels at about 300,000 kilometers every second. That is fast enough for a beam of light to circle the Earth several times in the time it takes you to blink. It is fast enough to go from the Earth to the Moon in roughly a second and a bit more. But the distances between stars and galaxies are so large that even this speed is not enough to make events look instantaneous. Because light travels at a finite speed, it always takes time to reach us. When you look at the Moon, you are seeing it as it was a little more than 1 second ago. When you look at the Sun, you see it as it was about 8 minutes ago. Those delays are so small that they hardly matter for our daily lives. You and I do not plan our day around the fact that we see the Sun with an 8-minute delay. But as soon as you extend the scale beyond the solar system, the delays become enormous. Astronomers use a unit called a light year to keep this straight. Despite how it sounds, a light year is not a unit of time. It is a unit of distance. 1 light year is the distance light travels in 1 year of continuous flight through empty space. If you wrote it out in kilometers, the number would be so large that it becomes awkward to use. So we keep the idea and drop the digits. A star that lies 10 light years away is a star whose light has taken 10 years to reach your eyes, or the detector of a telescope. Now, think about what that means for what you and I see. Suppose you are observing a star that is, say, 50 light years away. The photons hitting your eye tonight left that star around the time your grandparents were children, or perhaps even before they were born. You are literally seeing a memory of that star, not its present condition. If something dramatic happened to it yesterday in its own frame of time, you will not know for another 50 years. The effect becomes more striking as we increase the distance. The Andromeda Galaxy, a spiral galaxy, similar to our own, lies about 2 million light years away. When you look at a picture of Andromeda taken by a modern telescope, you are not seeing a contemporary portrait. You are seeing that galaxy as it was roughly 2 million years ago, when no members of our species yet walked the earth. There were hominin ancestors, certainly, but not humans in the modern sense. The light you see tonight left before anyone like you or me existed to receive it. Even farther out, we encounter objects called quasars, extremely bright active galactic centers powered by material falling into supermassive black holes. Some of the quasars we see are billions of light years away. Their light set out when the universe was only a small fraction of its current age. Observations from space telescopes such as Hubble and, more recently, the James Webb Space Telescope have collected light that has been in transit for more than 10 billion years. In those deep images, we are looking back to a time when the first generations of galaxies were just forming. The night sky, viewed with this understanding, becomes a kind of time map. Nearby stars tell you about the relatively recent past. Distant galaxies tell you about the distant past. The farther you look in space, the farther you look in time. There is no way around this, because there is no way for information carried by light to reach you faster than light can travel. This has an important consequence for how you and I interpret what we see. We cannot speak about the universe right now in any simple global sense, because now for us is different from now. For a galaxy, a billion light years away. By the time its present state could reach us, we would be far into our own future. All we ever have is a layered picture made of many different epochs, all arriving together at our location. It is worth pausing on what this means, even for the familiar stars above your head. Some of them are only a few light years away. Others are dozens or hundreds. They all appear side by side in a constellation, but they do not share the same timestamp. When you trace out a figure such as Orion with your finger, the light from its different stars left at different moments in history. You are unconsciously mixing light from different decades or centuries into one visual impression. Once you accept that the speed of light imposes this kind of delay, a natural question emerges: why this speed? Why is there a particular value that governs how quickly any light signal can move? In everyday life, we are used to the idea that speeds add and subtract. If you walk along the aisle of a moving train, someone standing by the tracks sees you move at the speed of the train, plus your walking speed. It is natural to assume that light should obey the same rule. Yet when experiments are done carefully, that is not what happens. You and I are led into a deeper puzzle. Light travels at a high but finite speed. That speed determines how far into the past we can see when we look at distant objects, and yet no matter how we move, we always measure the same speed for light in empty space. This combination of facts is what forced physicists at the turn of the 20th century to rethink their most basic ideas about space and time. There is another fact equally important that is less obvious from casual experience. No matter how you move, if you measure the speed of light in empty space, you always get the same result. This is not what our everyday intuition would predict. It is this clash between intuition and measurement that led one young physicist to imagine what it would be like to ride on a beam of light, and from there to reshape our understanding of space and time. At the end of the 19th century, many scientists believed that light must be a wave in some medium, much as sound is a wave in air or water. They called this hypothetical medium the luminiferous ether. In that picture, the ether filled all of space, providing a kind of invisible substance through which light waves could ripple. If that were true, the Earth would be moving through the ether as it orbits the Sunday. You and I might then expect to detect an ether wind in the same way a person sticking a hand out of a moving car window feels the rush of air. To test this, two physicists, Albert Michelson and Edward Morley, carried out a famous experiment in the late 1880s. They built a device that split a beam of light into two paths, sent them in different directions, and then recombined them. If the Earth were moving through an ether, light traveling along one path should be slightly sped up or slowed down relative to light along the other path. The interference pattern where the beams met would shift as the Earth moved in its orbit and changed direction relative to the ether wind. The result was not what the ether picture predicted. No matter how carefully they repeated the experiment, no matter how the Earth moved around the Sun, the speed of light came out the same in every direction. There was no sign of an ether wind at all. The natural conclusion was uncomfortable. Either the ether behaved in a very contrived way, or there was no ether at all, and light did not need a medium in the traditional sense. At about the same time, James Clerk Maxwell's equations for electricity and magnetism suggested that light in a vacuum should always move at a single characteristic speed. According to those equations, that speed did not seem to depend on who was measuring it or how fast the observer was moving. For many physicists, this was an odd mathematical curiosity. For a young patent clerk named Albert Einstein, it was a clue. Einstein liked to explore physics through thought experiments. One of his most famous mental pictures, which he later described, involved imagining himself running alongside a beam of light. He asked himself, what if I could move as fast as the light wave? In that case, if he looked at the wave, he would see its electric and magnetic fields standing still, frozen in space. But that could not be right. Maxwell's theory described light as an oscillating electromagnetic field, not as a static pattern. A frozen light wave would contradict the very equations that define light. This led Einstein to an important insight. Perhaps the problem was not with the equations, but with the assumption that he could ever catch up with the light. What if the universe simply does not allow any observer with mass to move at the speed of light? And what if instead of trying to adjust the behavior of light to fit our expectations about motion, we adjust our expectations about space, time to fit the measured behavior of light? Einstein gathered the experimental facts and the theoretical hints into two simple principles. The first is called the principle of relativity. The laws of physics are the same for all observers moving at constant speeds in straight lines relative to one another. There is no special privileged state of absolute rest. The second principle is the constancy of the speed of light Every such observer, no matter how fast they are moving, will measure the same speed for light in a vacuum. These two statements sound modest. They are easy to say and easy to remember. But if you and I take them seriously and follow their implications, they force us to abandon the idea of absolute time and absolute space. In our everyday experience, we assume that time flows uniformly everywhere the same for all observers, and that distances are fixed and independent of how we move. Under Einstein's principles, that picture cannot survive. If the speed of light is to remain the same for everyone, then different observers must disagree about distances and about time intervals in just the right way to keep that speed constant. This is the core of what Einstein published in 1905 as the special theory of relativity. It is special because it deals with observers moving at constant velocities, not yet with gravity or accelerating frames of reference. The theory provides a consistent way to calculate how measurements of time and space differ between observers moving relative to one another, while preserving the idea that the laws of physics do not depend on any particular state of motion. For you and me, the essential point is this: once we accept that the speed of light is a universal constant for all such observers, we can no longer think of time and space as separate rigid backgrounds. They are intertwined and they are flexible. Clocks can tick at different rates depending on motion. Lengths can be measured differently by different observers. The strange phenomena that follow from this time dilation length contraction and the relativity of simultaneity are not optional add-ons. They are required if the two principles are to hold together. There is something almost unsettling in how much of our everyday intuition we have to give up. At the same time, there is a certain clarity in it. Rather than inventing a complicated ether or forcing nature to fit our expectations, Einstein chose the simpler path. Keep the laws of physics the same in all constant speed frames. Keep the speed of light fixed, and let space and time adjust. The universe, it turns out, is less like a stage with a shared clock, and more like a network of observers, each with their own valid measurements, bound together by consistent rules. From this perspective, the speed of light is not just another high speed. It is built into the structure of reality as a limit, a conversion factor between space and time. That is why when we speak about look-back time in astronomy, we are really using light speed as a bridge between how far and how long. By now, you and I have accepted two ideas that are simple to state but hard to digest. The laws of physics are the same for all observers, moving at constant speeds, and the speed of light in a vacuum is the same for all of them. Once those ideas are in place, a natural question appears. If light has this special role, are we allowed to go faster than it? In ordinary life, we are used to pushing through limits. We built planes that broke the sound barrier. Why not build something that breaks the light barrier? At first glance, the analogy with sound is tempting. Sound is a wave in air or another material. For a long time, there was nothing that moved faster than sound in our everyday experience. Then engineers built aircraft that could accelerate past that speed. The transition was dramatic. Shock waves, sonic booms, new aerodynamic challenges, but it happened. It is easy to imagine the speed of light as just another barrier of that kind. Technically difficult, but not absolute. The problem with that analogy is that sound and light are fundamentally different. Sound needs a medium. Its speed depends on the properties of the air, or water, or solid through which it passes. You and I can change the speed of sound by changing the temperature, the density, or the material itself. Light in a vacuum is not like that. It does not need a substance to travel through. Its speed is not something we can tune by changing the stuff between the source and the observer. In the framework of relativity, the speed of light in empty space is a fixed feature of the way. Space and time themselves are connected. One way to understand why nothing with mass can reach or exceed that speed is to think about what it means to accelerate an object. To change an object's speed, you need to give it energy. At low speeds, this feels straightforward. Double the energy, and you can roughly double the speed. That matches your intuition about pushing a bicycle or accelerating a car. But as an object's speed gets closer to the speed of light, this simple relationship breaks down. Relativity tells us that as an object with mass moves faster, its resistance to further acceleration grows. You can think of it as if the object becomes harder and harder to push as it approaches light speed. The extra energy you supply no longer shows up as a big increase in speed. Instead, it shows up in other ways, such as an increase in the energy content associated with the object's motion. If you keep adding energy, the speed gets closer and closer to the speed of light, but never reaches it. The gains in speed become smaller and smaller for each additional step of energy you put in. You and I do not have to take this on faith. We have evidence from our own machines. Particle accelerators, large devices such as those at CERN in Europe or Fermilab in the United States, routinely push subatomic particles to speeds extremely close to that of light. Engineers feed huge amounts of energy into those particles using powerful electromagnetic fields. As a result, the particles' energies become thousands or even millions of times their rest energy. Yet when we look at their speeds, they remain slightly below the speed of light. Even with all the energy we can muster, they refuse to cross that line. If the speed of light were just another engineering challenge, these machines would have provided an easy way to break it at very small scales. They do not. Instead, every experiment has confirmed the same pattern. More and more energy yields less and less additional speed, with the speed of light acting as an unreachable ceiling. Cosmic rays, high-energy particles that come from space and strike the Earth's atmosphere tell the same story on a larger canvas. Some of these particles carry enormous amounts of energy, far beyond what we can produce in our accelerators. When we infer their speeds, they turn out to be extremely close to the speed of light, but still not beyond it. Nature, it seems, plays by the same rules we discovered in the laboratory. The speed of light also appears as a limit in a different way. It is the maximum speed at which information or influence can propagate. If you switch on a lamp, the fact that it has been turned on cannot affect something a light year away until a year has passed. No signal, no matter how clever, can outrun that delay. This is not just a statement about light itself. It is a broader bound on cause and effect. If you and I want to maintain the idea that causes must precede their effects in a consistent way, we must respect that limit. There is a more subtle feature hidden in all this. In relativity, the speed of light is not only a maximum speed, but also a conversion factor. It links units of distance and units of time in a consistent way. When astronomers talk about look-back time in billions of years, they are essentially using the speed of light to translate between how far away and how long ago. It is as if the fabric of the universe comes with a built-in ratio between space and time, and that ratio is expressed through this constant speed. For you and me, this means we have to abandon the hope of building a spaceship that simply goes faster than light to make long journeys quick. The laws of physics, as far as we can test them, do not allow it. That restriction can feel disappointing, but it also simplifies the rules. Rather than imagining a universe where different observers can send signals at arbitrary speeds, potentially scrambling the order of events, we have a consistent limit that keeps causality in place. Of course, this does not mean that motion near the speed of light is boring. On the contrary, it leads to some of the most counterintuitive effects we know. As an object approaches that speed distances measured along its direction of motion shrink according to observers at rest. Time intervals on clocks moving with that object stretch relative to clocks that remain at rest. The color of light from objects moving toward or away from you shifts. All of these phenomena are necessary to preserve the constancy of the speed of light and the form of the laws of physics. We have already glimpsed the idea that time and space must adjust themselves if the speed of light is to remain the same for all observers. Now we can see that treating this speed as a genuine limit forces those adjustments to be dramatic near that boundary. When speeds are low, the effects are tiny and can be ignored in ordinary life. As we approach the speed of light, they become dominant. By this point, you and I have agreed to something that would have sounded strange. A century and a half ago, the speed of light is the same for every observer, and nothing with mass can overtake it. That already bends our intuition, but relativity does not stop at a single surprising rule. Once you push anything close to that speed, the rest of our familiar ideas about size, color, and even what we see in front of us start to bend as well. This chapter is about those bends and about how we know they are real. In everyday life, if a car drives past you, the car does not look shorter, and its color does not shift into blue as it approaches and red as it recedes. The speeds involved are tiny compared with the speed of light, so the relativistic changes are far too small to notice. That is why our intuition remains safely classical. To see the full structure of relativity, we have to imagine speeds that are a significant fraction of light speed, and then ask two questions. What do we see from the outside, and what does a traveler see from inside the fast-moving frame? From the point of view of someone watching from rest, an object moving very fast in a straight line appears physically contracted along its direction of motion. This effect is called length contraction. It does not mean that the object really shrinks in some absolute sense, as if space itself were squeezing it. Instead, it reflects the fact that in relativity, observers moving relative to each other do not agree on what it means to measure the length at the same time. To determine a length, you need to know where the front and back are at one instant. Different observers slice space-time into instants differently. The result is that the moving object's length, according to the stationary observer's notion of simultaneity, comes out shorter. You and I cannot directly watch a spaceship and see it shrink, because we do not have ships that travel at such speeds. But the principle has been tested in other ways. In high-energy physics experiments, bunches of charged particles circulate in storage rings at speeds very close to light speed. From the perspective of the laboratory frame, the electric and magnetic fields associated with these bunches behave as if the bunches are compressed along their direction of motion. The equations that describe their behavior, the ones used at facilities like CERN and SLAC, match the predictions of length contraction. If engineers ignored these relativistic effects, their designs for accelerators would fail. The second major effect is the relativistic Doppler shift. You already know a non-relativistic version of it from sound. A siren sounds higher in pitch as it approaches and lower as it recedes. With light, something similar happens, but the details depend on relativity. When a source moves towards you at a significant fraction of light speed, the wavelength of light you receive is compressed. Shorter wavelengths mean a shift toward the blue or even ultraviolet part of the spectrum. When the source moves away, the wavelengths stretch, shifting toward the red or infrared. This is not theoretical decoration. Astronomers measure these shifts every day. Early in the 20th century, Vesto Slipher, and later, Edwin Hubble measured the spectra of distant galaxies and found that most of them are redshifted. The lines in their spectra are moved toward longer wavelengths compared with laboratory values. At the speeds involved for distant galaxies, most of the shift is due to the expansion of space itself. But the underlying idea that motion changes wavelength is the same. On smaller scales, we see relativistic Doppler effects in close binary stars, in the gas orbiting near black holes, and in jets launched from active galactic nuclei. In some quasars, the material in the jet moves so close to light speed that its radiation is dramatically brightened and shifted in frequency along the direction of motion. There is also a more geometric effect, aberration of light. If you and I stand still in a gentle vertical drizzle, the raindrops fall straight down. Start walking forward and the rain seems to slant toward your face. It is not that the rain has changed its path. Your motion changes the angle at which the drops hit you. Light behaves in a similar way. When you move at high speed, photons that were originally arriving from many directions are aberrated into a narrower cone in front of you. In the limit of speeds, very close to the speed of light, nearly all the visible light from the universe is aberrated into a small region around the forward direction. The sky would seem to crowd into a bright, distorted patch ahead. Computer simulations have made these ideas more concrete. Teams at places like Carnegie Mellon University have generated visualizations of what a landscape would look like if you could ride a vehicle at 90% or 99% of light speed. Straight roads appear to curve. Objects that you have already passed still seem to hang in front of you at the edges of your view. Colors at the center of your motion shift toward blue, while those behind you shift toward red. The entire scene appears tunnel, like a direct result of aberration and Doppler shifting acting together. All of this still describes what observers see from different frames. From your own perspective, if you were inside the fast-moving ship, you would not notice your own length contracting. Measuring rods and clocks that move with you would seem unchanged, because you would be using them as your standards. You would, however, notice the outside world behaving oddly. Distances along your direction of motion would seem compressed. Light from stars ahead would be bluer and brighter. Light from behind would fade and redden. The distribution of light over the sky would no longer be uniform. These are not merely curiosities. They are necessary adjustments to keep the speed of light the same in every inertial frame while preserving the structure of the laws of physics. If lengths did not contract, and if frequencies did not shift in just the right way, observers moving relative to one another would measure different speeds for light in vacuum, and the central principle of relativity would fail. Instead, everything fits together. Altered lengths, shifted colors, and changed viewing angles combine to keep the rules consistent. For you and me, the important takeaway is that motion at relativistic speeds does more than make things go faster. It reshapes our measurements of space and our perceptions of light. On human scales, these effects are so small that we are free to ignore them. At the scale of cosmic rays, binary stars, and particle beams and accelerators, they dominate. The universe does not quietly transition from one regime to the other. It follows a single set of rules across all speeds. We only start to notice the full structure when we move close to the limit. There is still another piece of the story, though. We have focused on distances, colors, and directions. But relativity does not only adjust space, it also acts on time. Moving clocks do not tick at the same rate as clocks at rest. Processes that would normally decay quickly can be sustained for longer when they move close to light speed. In other words, motion affects aging, not just shape and color. There is one remaining consequence that is both simple to state and deeply unsettling. A moving clock does not tick at the same rate as a clock at rest. If you travel fast enough and return, you can, in a precise sense, come back younger than the people who stayed behind. That is not a science fiction slogan. It is a direct consequence of the same principles we have been following since Einstein. The starting point is straightforward. In special relativity, each observer carries their own time, measured by a clock moving with them. For you, that clock might be your heartbeat, a wristwatch, or the oscillations of atoms in an atomic clock. The theory predicts that if you move at a high constant speed relative to someone else, your clock and theirs will not agree on how much time has passed between two events. The moving clock will have recorded less time than the clock that stayed in the rest frame. You can picture this as follows. Imagine a simple clock built from light itself, a mirror at the top, a mirror at the bottom, and a pulse of light bouncing between them. Each round trip of the light pulse marks one tick. If the clock is at rest, relative to you, the light simply moves straight up and down. If the clock is moving sideways, relative to you, the light must follow a diagonal path to keep hitting the mirrors. That diagonal path is longer, yet because the speed of light is fixed, it takes longer for the light to complete a round trip. The moving light clock ticks more slowly in your frame. You and I do not carry light clocks in our pockets, but the argument applies to any physical process that can serve as a clock. Once you accept that the speed of light is the same for everyone, the geometry of space-time forces moving processes to unfold more slowly compared with similar processes at rest. This effect is called time dilation. The faster you move relative to someone else, the larger the discrepancy in elapsed time. The famous twin paradox is really just an illustration of this rule. Imagine two identical twins. One remains on Earth. The other boards a spacecraft that accelerates to a speed close to that of light, travels for some time, turns around, and returns. According to special relativity, the traveling twins clock has ticked fewer times than the stay-at-home twins clock. When they reunite, the spacefaring twin is biologically younger. There is no real paradox in the mathematics. The paths they take through space-time are different, and those different paths have different durations. The only paradox lies in our expectation that time should be absolute and shared. You and I might reasonably ask, is this just an elegant story, or is there evidence? There's a great deal of evidence, and it comes from multiple sources. One of the clearest involves particles called muons. Muons are unstable. At rest, they decay on average in about 2/millionths of a second. That lifetime can be measured in laboratories. But muons are also produced high in the Earth's atmosphere when cosmic rays hit atomic nuclei. Those muons travel toward the surface at speeds close to the speed of light. If we used their lifetime at rest and the distance to the ground, we would conclude that most of them should decay before reaching detectors at sea level. Yet when instruments were set up on mountaintops and at sea level, in experiments such as those by Bruno Rossi and David Hall in the 1940s, many more muons were observed reaching the lower detectors than a classical calculation would allow. Relativity resolves the discrepancy. From the point of view of the Earth, the muons' internal clocks run slow because they are moving so fast. Their 2-microsecond lifetime is stretched into a longer interval, giving them enough time to make the journey. From the muon's own point of view, something equivalent happens in space. The distance through the atmosphere is contracted. Either way, the combination of time dilation and length contraction allows the particles to reach the ground in full agreement with experiment. Another line of evidence comes from precise clocks carried on aircraft and satellites. In the early 1970s, Joseph Hayfel and Richard Keating flew atomic clocks on commercial airliners around the world, and then compared them with reference clocks kept at the United States Naval Observatory. The flying clocks showed small but measurable differences in elapsed time, consistent with the predictions of relativity when both their velocities and altitude-related gravitational effects were taken into account. Modern versions of this experiment are much more accurate. Laboratories such as the National Institute of Standards and Technology in the United States and similar institutes elsewhere routinely compare atomic clocks in different locations, and they must include relativistic corrections to interpret the results. The global positioning system which you and I rely on every time we use satellite navigation would drift out of alignment if these effects were ignored. GPS satellites orbit the Earth at high speed and at altitudes where the gravitational field is weaker than at the surface. Both special relativity due to their motion and general relativity due to the difference in gravitational potential affect the rate at which their onboard clocks tick. Engineers pre-adjust those clocks and apply continuous corrections so that as seen from the ground, they remain synchronized. Without these relativistic adjustments, your receiver's calculated position would quickly wander by kilometers. For me, these examples make time dilation feel less like an exotic curiosity and more like a practical fact. High-energy physicists, metrologists, and navigation engineers do not invoke relativity because it is philosophically interesting. They invoke it because their instruments and systems demand it. The clocks and particles obey the same rules that Einstein wrote down in 1905, and they do so with a precision that leaves little room for doubt. All of this returns us to the original question: can you and I use this effect to travel into the future? In a sense, yes. If you could ride in a spacecraft that travels very close to the speed of light for an extended period, and then return, your personal time between departure and arrival could be much shorter than the time elapsed on Earth. You would have aged less than those who remain behind. From your standpoint, the journey might last, say, a couple of decades. From Earth's standpoint, centuries or more might have passed. You do not move backward along anyone's timeline, but you do jump forward relative to the people who stayed at home. This is more than a thought experiment. The same mathematics that explains muon lifetimes and GPS satellite clocks applies to any world line, including that of a human traveler. The challenge is not theoretical, but technological, building a system that can safely sustain near light speed travel for macroscopic objects like spacecraft and their crews. If time dilation makes high-speed travel theoretically useful, You and I still face a harder question: how do we accelerate a real spacecraft to such extraordinary speeds in the first place? Human history contains a pattern worth noticing. Ideas often appear long before the technology needed to realize them. Leonardo da Vinci sketched flying machines in the 15th century, 400 years before aircraft became practical. His drawings are filled with details about wings, pulleys, and mechanical muscles, but he lacked the engines and materials needed to lift a person off the ground. The idea arrived early. The tools arrived late. In the 20th century, something similar happened with interstellar flight. As soon as we understood how far away the stars are, engineers and physicists began imagining propulsion systems powerful enough to cross those distances. The proposals were not science fiction. They were grounded in known physics. What these early studies lacked was not imagination, but political, economic, and technical feasibility. If you and I look at them now, we see serious attempts to confront the energy problem head-on. One of the most ambitious designs was called Project Orion, conceived in the late 1950s by a team that included Stanislaw Ulam and later discussed by Freeman Dyson. The idea behind Orion was startlingly direct: use a series of nuclear explosions as a means of propulsion. The spacecraft would ride behind a massive pusher plate, and each controlled detonation would push the plate forward, giving the ship a steady rhythm of impulse, almost like a cosmic piston engine. The physics behind this approach is sound. Nuclear explosives release an enormous amount of energy in a tiny volume, far greater than any chemical fuel. In principle, Orion could reach about 1/10 the speed of light. From a scientific standpoint, Orion was viable. The barriers were elsewhere. No nation was willing to detonate hundreds or thousands of nuclear devices in space, partly because of treaty restrictions and partly because of the obvious environmental and political consequences. For you and me, the lesson is that some propulsion ideas are limited not by physics but by human context. Around the same time, engineers at the British Interplanetary Society began studying another design known as Project Daedalus. This concept avoided nuclear bombs and instead envisioned a fusion-powered engine. The idea was to use pellets of nuclear fuel, helium-3 and deuterium, compressed and ignited in rapid sequence by high-energy beams. Each miniature fusion event would create a burst of hot plasma to push the spacecraft forward. Daedalus was designed as an uncrewed probe intended to reach a nearby star, such as Barnard's star, within roughly 50 years of flight time. The engineering study published in the 1970s remains one of the most detailed interstellar mission proposals ever produced. Fusion propulsion has the appeal of extremely high energy density and high exhaust velocity. It also has a major obstacle-controlled fusion reactors capable of continuous power production do not yet exist. Laboratories such as the Joint European Torus and the National Ignition Facility have made progress toward fusion burn, but none have produced sustained net power suitable for an engine. The Daedalus study showed what could be built if fusion technology matures. It did not pretend that such technology already existed. Even if we set nuclear and fusion concepts aside, physics-driven ideas continued to emerge. In the 1960s, physicist Robert Bussard proposed the interstellar ramjet. The design imagines a spacecraft carrying a vast electromagnetic field structure hundreds or even thousands of kilometers wide that would scoop up the thin hydrogen gas found between stars. As the ship moves forward, it gathers this interstellar hydrogen, compresses it, and uses it as nuclear fusion fuel. In principle, such a ramjet could accelerate as long as there is hydrogen to collect. This makes it something like a jet engine operating between the stars, rather than within an atmosphere. The physics behind Bussard's idea is sound, but the challenges are severe. Measurements by spacecraft such as Voyager and IBEX have shown that the density of interstellar hydrogen is extremely low, roughly 1 atom per cubic centimeter. That means the scoop would need to be enormous, and the magnetic fields required would be far beyond anything we can generate today. Later analyses by T.A. Heppenheimer and John Fishback pointed out that such a ramjet would also face extreme heating and radiation challenges as it approached relativistic speeds. Still, the concept remains valuable as an exploration of what the laws of physics permit. A theme emerges from all these studies. None of them rely on imaginary physics or violations of relativity. They all accept the same natural limits you and I have been discussing. They differ in the engineering strategies they propose for collecting, storing, and converting energy. They also differ in their willingness to assume technologies we do not yet possess. Orion assumes political conditions we do not have. Daedalus assumes fusion capabilities we have not yet achieved. The ramjet assumes magnetic and structural technologies far beyond our current reach. Yet together, these examples show that the idea of reaching 10% of light speed is not absurd. It is difficult, expensive, and currently beyond our engineering capacity, but not forbidden by known physics. If you and I project forward by a century or two, assuming steady progress in energy systems, propulsion research, and materials science, it is not unreasonable to imagine a first generation of interstellar probes built along these lines. Even so, 10% of light speed is not enough to cross the Milky Way or to reach another spiral galaxy in a human lifetime. At such speeds, it would take decades just to reach the nearest stars and tens of thousands of years to traverse any meaningful portion of the galaxy. If the dream is to allow a crewed mission to experience distant destinations within a single personal lifetime, we need something beyond these first-order designs. We have to confront the idea of sustained, near-relativistic acceleration. The key is time dilation. Special relativity tells us that when you move very fast, your own proper time, the time measured by a clock that travels with you, can be much shorter than the time measured by observers who stay behind. If we combine that with a continuous comfortable acceleration, we get a remarkable result. In principle, a human crew could cross tens of thousands of light years within a few decades of ship time, even though far more time would pass in the rest of the universe. Physicists and science communicators have been exploring this idea since the mid-20th century. If you look at the work of Hermann Bondi, for example, or later popular expositions by authors like Robert Forward, you find the same basic scenario. A relativistic rocket that accelerates at about 1 g. The acceleration you feel standing on Earth's surface, that value is not chosen at random. 1 g keeps the crew comfortable. It provides artificial gravity along the direction of the ship's thrust and avoids long-term health issues associated with weightlessness. Imagine you and I aboard such a ship. We start from rest relative to the Earth and fire up an engine powerful enough to maintain 1 g of thrust. For the first part of the journey, we accelerate. To us, inside the ship, it feels like normal gravity pulling us toward the floor, which is actually the rear of the vessel. As our speed increases, clocks on Earth, if we could watch them from a distance, would appear to tick faster and faster, while our own onboard clocks would feel normal. After reaching some midpoint in the journey, we would turn the ship around and thrust in the opposite direction, still at 1 g. Now the acceleration acts to slow us down in the external frame, but for us, it still feels like steady gravity. When we arrive, we come to rest, relative to our destination. The interesting part is the comparison of times. In the Earth's frame of reference, the entire journey might take tens of thousands of years if the distance is tens of thousands of light years. In the frame of the ship, because of time dilation and length contraction at high speed, the trip might span only a few decades. Different authors plug in different numbers, but the pattern is robust. Calculations published in relativity textbooks and papers show that with sustained 1g acceleration and deceleration, you could in principle reach the center of our galaxy, about 26,000 light years away, in a few decades of ship time. By the time you return, however, something like 50 or 60,000 years might have passed on Earth. This is not magic. It is the inevitable consequence of how space-time intervals work in special relativity. World lines paths through space-time have different lengths in time depending on their shape. The path of the ship is not the same as the path of someone who stays on Earth, so the elapsed proper time is different. You and I are already familiar with this idea from the twin scenario. Here we are simply extending it to interstellar scales and sustained acceleration. Of course, building a rocket that can accelerate at 1g for years is an enormous challenge. The energy requirements are staggering. Even using idealized propulsion, such as an extremely efficient antimatter engine, or a perfect fusion drive, the mass of fuel required grows rapidly with the desired final speed and the need to decelerate at the far end. Researchers such as Eugen Sanger and later more modern authors have worked through versions of the relativistic rocket equation in plain language. The higher the fraction of light speed you aim for, the more extreme your energy needs become. From a practical engineering standpoint, this kind of ship is far beyond anything we can build now. But from a physics standpoint, the idea is sound. It does not violate any known principle. The speed of light remains the limit. The ship never exceeds it in any inertial frame. Time dilation and length contraction do the rest. From the ship's vantage point, the distances along the direction of motion shorten as the speed increases. What looks like 26,000 light years in the galaxy's frame can look like a much smaller effective distance in the ship's frame, precisely because of length contraction. Combined with the slower ticking of the ship's clocks, as seen from outside, this allows the crew to cross the contracted distance in what feels to them like a manageable span of years. If you and I project this to even larger scales, the consequences become extreme. In some calculations, idealized but consistent with relativity, a traveler could in principle make a round trip across large portions of the observable universe within a human lifetime of proper time, provided they endure continuous high acceleration and deceleration, and have access to unimaginable amounts of energy. When they return, however, the universe they came back to would be billions of years older. The galaxies would have evolved, stars would have been born and died, and perhaps even the overall structure of the cosmos would have changed. This picture raises questions that are more philosophical than physical. What would it mean psychologically and culturally to leave behind not just a planet but an entire era? A crew that undertakes such a journey would know from the moment they depart that they are separating themselves from their original timeline. For them, the trip is a long but finite experience. For those who stay, it is a leap far into the future. Every relativistic voyage of this kind is a one-way trip in time, even if the ship returns to its original location in space. You and I should also be clear about what this does not do. It does not permit travel into the past. No matter how cleverly you arrange your acceleration, your world line always moves forward in time. You can choose a path that gives you less proper time between events than someone else's path, but you cannot bend that path back to intersect your own past in a way that allows you to change it. The ordering of cause and effect remains intact. Still, the idea of using relativity to jump ahead invites speculation. If we can move so far into the future by traveling near light speed, could some other configuration of space-time allow us to move backward? Could there be routes through curved regions of space-time, or through exotic structures like wormholes that deflect a world line in such a way that it meets its own history? Once you and I accept that relativistic travel can propel a crew far into the future, it is natural to ask the more ambitious question, could anything in physics allow us to go the other way? Could we ever reach into the past? This idea challenges more than engineering. It cuts into the foundations of cause and effect. It also exposes how fragile our historical narratives would be if the past could be changed, even in small ways. A common way to explore the issue is to imagine a dramatic intervention. Suppose someone traveled back far enough to prevent a major historical event, say stopping Christopher Columbus from securing the funding that launched his Atlantic voyage in 1492. Would that change the world dramatically? Or would the underlying tides of economics, navigation, and international competition have driven some other explorer to make a similar crossing soon after? Historians tend to favor the second view. Although Columbus played a decisive personal role, the conditions that made his journey possible were not unique to him. Several scholars, including historians such as Felipe Fernandez Armesto, have noted that maritime expansion was already an accelerating trend in late 15th century Europe. Even without Columbus, the Atlantic would almost certainly have been crossed within the same generation. Physics frames the problem differently. Instead of asking which human events are fragile or robust, it asks whether the structure of space-time even permits a world line, your path or mine, to loop back and intersect its own past in a controllable way. Special relativity does not allow this. World lines tilt, stretch, and differ, but they always move forward in time. Once we add gravity, the question becomes more subtle. Einstein's general theory of relativity, published in 1915, allows space-time to curve. In curved space-time paths can bend in ways that would never be possible in a flat geometry. This opens the door mathematically to solutions that contain closed time-like curves paths that return to their starting point in time as well as in space. A few of these solutions are famous. In 1949, Kurt Gödel found a rotating universe model in which the global rotation of matter allows closed time-like curves everywhere. In the 1930s, Willem Jacob van Stockham and others explored rotating cylinder solutions that also permit such curves. These examples are mathematically consistent but physically unrealistic. Gödel's universe has properties that do not resemble the one we observe. The rotating cylinder would require infinite length and impossible stability. What they show is not that time travel exists, but that general relativity's equations do not automatically forbid exotic possibilities. The discussion became more concrete in the late 20th century when physicist Kip Thorne and colleagues at Caltech examined whether a wormhole could be used as a time machine. A wormhole, in its simplest description, is a hypothetical tunnel connecting two distant regions of space-time. Thorne's group showed that in principle, if one mouth of a stable wormhole were accelerated to high speed or placed in a strong gravitational field time, dilation would cause the two mouths to age at different rates. Someone could then travel through the wormhole and emerge at an earlier time relative to an outside observer. The idea was used as a plot device in Carl Sagan's novel Contact with Thorne's guidance, ensuring that it followed the underlying physics. But all wormhole models share a critical issue. Keeping the tunnel open requires forms of matter with properties not known to exist in nature. Specifically, the throat of a traversable wormhole must be threaded with exotic matter that has negative energy density relative to the vacuum. Quantum field theory does allow small regions of negative energy under special conditions as seen in the Casimir effect, but sustaining such energy densities on macroscopic scales remains hypothetical. Thorne himself has been cautious, noting that these structures might exist only in the mathematics of idealized spacetimes, not in actual astrophysical environments. Long before wormholes entered the discussion, physicists had already recognized deeper problems with time travel. If closed time-like curves exist, they allow causality violations, situations where an effect appears to precede its cause. Stephen Hawking famously proposed a chronology protection conjecture, suggesting that the laws of physics might conspire to prevent such curves from forming in the real universe. He pointed out that quantum fluctuations near the entrance of a potential time machine could grow uncontrollably, collapsing the geometry before any paradoxical event could occur. While this idea is not proven, it illustrates the strong belief among many physicists that the universe disfavors causal loops. For you and me, this raises a practical question. Even if time travel into the past were allowed by some exotic solution of general relativity, would it matter? Would the past be malleable? The historical example of Columbus suggests that changing an individual decision might not break the overall momentum of the period. Many events in history are robust outcomes of broader conditions, economic pressures, technological levels, climate patterns, or competition among states. But at smaller scales, history is full of contingencies. A slight mutation in an ancient organism, a small asteroid missing or striking Earth, or a shift in a local climate pattern could have pushed biological evolution along a different branch. In that sense, the fine details of the world we inhabit are sensitive to chance events that could easily have gone another way, even without time travel. This tension between robust trends and fragile details is central to the Ionian what-if. The Ionian Greeks of the 6th and 5th centuries BCE, thinkers such as Thales and Anaximander, and later Democritus, pursued natural explanations of the world that resemble scientific reasoning. Their tradition was powerful but short-lived. If it had continued without interruption, if experimental inquiry had been institutionalized and passed through generations, if empirical methods had matured instead of being overshadowed by other philosophical currents, then the scientific revolution might have occurred centuries or even millennia earlier. In that alternate timeline, you and I might already live in a civilization that travels between stars, guided by a scientific tradition far older than our own. Speculation aside, the real universe offers no evidence of anything that would let us rewrite the past. We can leap forward in time by moving fast, but no experiment has ever demonstrated a route backward. The foundations of relativity, the behavior of quantum fields, and the structure of causality all point toward the same conclusion: the past appears fixed. Not because history is rigid, but because the geometry of space-time leaves no accessible paths that lead there. You and I have spent a long time thinking about motion time and the large-scale structure of the universe. Now it is worth asking a more local and in some ways more personal question. How did this particular planetary system form, and how contingent was the path that led from a cloud of gas to you and me, sitting here thinking about it according to multiple lines of evidence, from meteorites, from radioactive dating, and from observations of young stars, the story of our solar system began about 4.5 billion years ago. A small region inside a giant molecular cloud, rich in hydrogen, helium, and heavier elements forged by earlier generations of stars, began to collapse under its own gravity. Most of the material fell toward the center, forming what would become the Sunday. The rest flattened into a rotating disk of gas and dust, the solar nebula. Within this disk, particles of dust and ice stuck together. At first, the forces involved were small electrostatic attractions, gentle collisions, but as clumps grew, gravity began to dominate. The result was a swarm of planetesimals, kilometer-sized bodies on intersecting orbits. These smashed into one another, sometimes shattering, sometimes merging, gradually building larger objects, protoplanets. The process was chaotic. The early solar system was not a calm clockwork, but a violent environment where collisions, scattering events, and near misses were routine. Models of this era, supported by studies in planetary science, suggest that many potential worlds were destroyed or ejected before the system settled into its present configuration. The structure we see today, 4 small rocky planets in the inner region, 4 giant planets farther out, a belt of asteroids and distant icy bodies, is just one outcome among many that could have occurred. Simulations of planetary formation show that small changes in initial conditions can lead to very different architectures, no inner rocky planets at all, or multiple super-Earths very close to the star or giant planets migrating inward and scattering smaller bodies. Observations of exoplanet systems confirm this diversity. Missions like Kepler and TESS have revealed thousands of planets orbiting other stars, many of them in arrangements very unlike our own hot Jupiters, skimming the surfaces of their stars, compact systems of super-Earths, mini-Neptunes, and worlds in circumlunar orbits around 2 suns. From that perspective, the fact that you and I live in a system with a relatively stable circular orbit for Earth inside the region where surface water can remain liquid is not something guaranteed by any simple rule. It is the outcome of a specific sequence of events. The position and mass of Jupiter, for example, appear to have influenced the distribution of material in the inner solar system, limiting the growth of a planet in the asteroid belt, and perhaps deflecting some comets and asteroids away from Earth while sending others inward. Studies of meteorites and crater records indicate that large impacts have repeatedly altered the course of our planet's history. Life emerged on this unstable stage and then evolved over billions of years. The fossil record shows long periods of gradual change, punctuated by mass extinctions. The event that ended the age of the non-avian dinosaurs, likely triggered by a large asteroid impact and associated environmental shocks, cleared ecological niches that mammals later filled. If that impactor had missed or arrived at a different time, the dominant large animals on Earth today might be very different, and the branch of the evolutionary tree leading to humans might never have flourished. The same physical laws would still operate, but the details of climate ecology and evolutionary pathways would shift. When we combine this with what we now know about exoplanets, the picture becomes even sharper. As of now, astronomers have confirmed over 6,000 planets beyond our solar system, with thousands more candidates waiting for verification. NASA and other groups classify many of these worlds into types that do not exist in our system. Super Earths between about 2 and 10 times Earth's mass mini. Neptunes with thick envelopes, and hot Jupiters so close to their stars that their atmospheres are heated to extreme temperatures. Instruments like ALMA, Kepler, and TESS have shown us that planetary systems come in a wide range of shapes, densities, and dynamical histories. Some are relatively flat and ordered. Others bear the marks of migration and disruption. Our configuration, temperate rocky planet, large moon gas giants at moderate distances, is one arrangement among many possible ones. The atoms that make up your body and mine are also part of this story. Hydrogen in our water and organic molecules dates back to the early universe. Heavier elements such as carbon, nitrogen, oxygen, and iron were forged in previous generations of stars and distributed into space by stellar winds and supernova explosions. So when we say that we are star stuff, we are not being poetic alone. We are making a precise statement about chemical origin. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all were built by nuclear reactions in stars and then reshaped by planetary chemistry. For you and me, the lesson in all this is not that Earth is the only possible home for life. On the contrary, the sheer number and variety of planets we now know exist suggest that habitable conditions may arise in many places. What the solar system's history shows is that any particular outcome, this orbit, this climate history, this sequence of extinctions and innovations, is the result of a chain of events that could have been different at many points. Physical law sets the boundaries. Within those boundaries, chance and history matter. What this journey leaves us with is not a conclusion, but a clearer sense of where we stand. The universe is ancient, dynamic, and governed by rules we can test and understand, and yet the particular conditions that made our world, its orbit, its chemistry, its biological history, were not guaranteed. Law and contingency work together, from the movement of galaxies to the molecules that allow you and me to think at all. Thank you for spending this time tracing that arc with me. If nothing else, I hope this journey leaves you with a steadier sense of the cosmos. We inhabit not distant or abstract, but something we are built from and still connected to every time we look up.